Okay, so starting to look at, in this lecture, actual computational tools, kind of extending beyond just the spreadsheet style analysis to sort of thinking about what are additional things we can do with spreadsheets, and then why would we extend into the types of tools we'll introduce in the next lab. So this will actually fold in pretty well with lab 3 on Monte Carlo analysis. We'll talk a little bit about Monte Carlo here. But before that, just a reminder, homework B1 is due Saturday. There is a bonus. One of the few times I think on the homeworks there's a bonus. So you may want to take advantage of that. There's this interactive Canvas activity is available. It's due before lecture D1. And homework C2 is available. You will technically have enough knowledge to do homework C2 after lecture C2. So that's after the next lecture. So you feel free to give that a shot. And what we'll talk about next time will relate directly to that homework. Otherwise, the reminder about the Rockwell competition in the fall session, entry forms are due end of September. So any questions, administrative questions? All right, great. So last time we talked about, sort of the bonus for homework B1 that, we have to understand the hand simulation so that we know, you actually can go into Arena and look at its event calendar. So you have to understand where that comes from. And sometimes it helps you in debugging the program and figuring out why things are being scheduled, when they're being scheduled, if they're being misscheduled, those sorts of things. So it's important to know what's going on behind the scenes, which is why you do the hand simulation. But of course, that's impractical for you to be trying to do that sort of simulation by hand. There are some interesting examples back in the 40s and 50s of people doing computational work before computers were available and like setting up, checker pieces and coins on coffee tables and flipping them with certain probabilities and actually manually doing the types of things that we now ask computers to do. But generally speaking, that hand sim is for you to learn the methods, not to be useful. But you can set up relatively effective spreadsheets that are able to solve the types of problems we want to solve without special purpose tools. And so that's kind of what that bonus was about, is that we can say, well, for this so-called MM1Q, so if you haven't hit this yet in 470, when you talk about queuing nodes and queuing networks, then you name the nodes based on things like their arrival rate, on their service rate, and how many servers are there. So MM1, as you'll learn in 470, M basically means you have exponential inter-arrival times. So the inter-arrival durations are exponentially distributed. The second M means you have exponential service times. And then the 1 means you have 1 server. So if we're simulating a MM1 queue node, these are the inputs that we generate. And so for that, the homework B1 bonus is for you to simulate using a spreadsheet these sorts of stats for an MM1 queuing node. And so, we went through that last time, so I'm not going to step through that whole process. But the idea there was that rather than thinking about how the system moves through time, you think about what are the relationships over time that always hold across all the customers. So we can ask questions about the customers that are our entities. We ask questions about entities. And so we can say, when did the customer arrive? When did their service begin? How long did they wait in the queue? When did their service end? How long they spend in the system? And then we can ask some things about the utilization of the system. How idle was the system? So these are things we can ask, but rather than modeling them through time where we're actually building the trace like we would in a hand simulation, in this case, we're saying what relationships always hold, and then let the spreadsheet populate this. And so that's what we did last time. We said, well, every column of this, we can just say has a relationship to the previous row. And so now if we populate all of those relationships, we can populate the whole table. And this has all of the same information that your hand simulation is in it. So that's one example of how to use a computational tool to handle these discrete event system simulations. And I think it's notable because there is no notion of state in a spreadsheet. You can't say, what is the state of the spreadsheet now? What is the state of the spreadsheet later? It is just purely based on relationships. And yet it's able to generate all of the data you would get if the system was running in time. So that's what you get to practice on that homework. And you should be able to check the hand simulation that all the data you generated in your hand simulation shows up down here and vice versa in your spreadsheet. So that's what we talked about last time. So with that in mind, are there any questions about that process and where we are before we get to where we're going? Okay. So I want to make things a little more complex. So as I mentioned in 470, you'll learn that you can have these queuing nodes that are characterized by this Kindle's notation, where these first two are the input models, and this third one is the number of servers. Well, we might want to make this a little more complicated. What if we're not dealing with a queuing node that only has a capacity of 1? What if it has a capacity of 2? So now you've got arrivals coming in, and they either can go to server A or server B. So if server A is busy, they go to B and vice versa. So how does this change the dynamics of the system? How does this change the statistics? We might expect that by adding another server, that the waiting time on average for the customers go down. But that sort of assumes that the arrival rate is sufficiently high that you're going to need both servers. So we may not know that ahead of time. Now you're going to learn things in 470 about Little's law and some other stuff like that that'll help you predict, whether the system, what sorts of lines you might expect before even running this. But if you really want to know what's the maximum length of the queue, what's the minimum length of the queue, all of these sort of transient features, like how bad can it get in the system, then you may need to simulate the system. And so that's what we're gonna do here. And so in this example, which I'm borrowing from the bank's textbooks, this is from chapter 2, I'm gonna call server A Able and server B Baker. And so that's in the spreadsheet that we're going to see. We're going to see Able and Baker. And what we'll see is we can do the exact same thing we do in the bonus for homework B1 to simulate this more complex system. We just have to think a little bit more about these relationships. But it still comes down to asking questions about, in this case, it's not customers, they're calls to a call center. So we have calls arriving, but they may as well be customers arriving. So in this case, we can ask questions about the calls. So we can say, what is the time between calls? That's an input that has to be given to us. We can say, how long did that call take? Well, you can say, well, this is a call about billing. Billing calls come from a certain distribution. This was a call about tech support. Tech support comes from a different distribution, and so on and so forth. So that's all known ahead of time. So for each one of these calls, we can figure out how they're spaced and how long they're going to take once they hit a server. But then we can ask questions about things we don't know about, like when are they going to arrive? Well, that should be easy to calculate. But then, when is the next server available? If we know that, then we can figure out which server this customer will eventually go to. So that's useful information to know. And then that allows us to populate the server chosen. Time service begins. So that goes right back to our first spreadsheet. We want to know, when did this call actually start getting handled? So that will tell us how long they waited. And then next, completion time. So if we know which server is handling which customer, and we know the customer's service time, we'll know when the servers will be ready for their next customer. And that's going to somehow allow us to populate when the server is going to be available. And then finally, the kind of stats on how long did the caller wait and how long did they spend in the system total. So we just want to set up relationships to populate this table the same way we did before. And it's going to look very similar. So this arrival time is identical to what we did before. The next arrival time is just the previous arrival time plus the inter-arrival time for that customer. So 2 here, we get that because we're taking the previous time, 1, plus the inter-arrival time, 1, that gives us 2. 2 plus 3 gets us 5, 5 plus 2 gets us 7. So this is just a cumulative sum of the inter-arrival times, same as we did with the MM1 queue. So we get a little more complex here to figure, all right, now that we have 2 servers, then I would like to know which server was picked for this caller, because that's going to tell me things about how long the caller is going to be with that server. So if I had the other information in the spreadsheet, this would be the relationship that would determine that. I would say Abel is chosen for a caller if the time Abel is available is before the time Baker is available, and vice versa. So for every caller, I said, I theoretically, once this is done, if I do it right, for every caller, I should be able to ask for that caller, when is the next time each server will be available? And this caller might have arrived at time 5. Abel might be available at 6, Baker available at 9. Well, Abel is going to be available sooner than Baker, so this caller is going to get routed to Abel. So that's all we're saying here. But we still need to figure out how to populate this. So that's going to be, but theoretically, if we had these columns, we could calculate this column. So time service begins. So we will eventually go back and populate these. But now that we know server chosen, I'm just going to work this way before we go back and repopulate this. So then time service begins. Well, that is just going to have to do with whether we arrive to a busy system or an idle system. So if we look at the minimum of the two servers when they're available, that's the next time any service can be done. If we arrive and our arrival time is, so it's the max here. So if our arrival time is after the next time a server is available, then that means we can immediately, that means we will be the max. So we'll immediately be able to get in because the servers will become available before we arrive. Alternatively, if our arrival time is less than the minimum of these two availability times, then it's the other way around. We arrive and nobody's available. We have to wait until they're available. So that's how we figure out when the service begins. And we can populate that column. Okay, so then we can move on. And again, we'll eventually come back to when the server's available, but we end up having to calculate this stuff first before we can go back to when the server is available. So at the next completion time, we now have enough information to write down that relationship. So as we can say that for Abel, the next completion time is going to be whenever the current, so this is if Abel is chosen. So for Abel's next completion time, we're saying for this caller was Abel chosen. That's what this is marking here and saying for this caller, if Abel was chosen, then it's going to be this caller's service beginning time plus however much time this caller needs to complete their service. So, but if it's otherwise, if we're talking about Abel's completion time, but Baker was chosen for this one, then we have no information about when Baker's going to be done because that doesn't relate to this customer. So for this column here, that's why you see pairs 4, 4, 7, 7, 12, 12, because it tends to be that they go back and forth between Abel and Baker, Abel and Baker. And so whenever you're in a row where the other server was chosen, then you just copy down your completion time because that new customer or that new caller doesn't affect your service. And so your next service time is whatever it used to be. So that's where we get that logic. And then we flip that logic for Baker's completion time. So now for the Baker column, we ask about if Baker was chosen, then that's when we do the math. And if Abel was chosen, that's when we just pass it down. Questions about any of that so far? Basically the same thing we did with the MM1 queue, but we just have to now take that one server that we knew was the only resource they were competing for, and then say, now we've got two resources available. We need to figure out for this caller, what resource are they using? And that's all we're doing so far. Okay, so now that we have all of that, we can go back. And so here, it's pretty easy to say that if we know for every caller when the servers will be available, so we know for, let me say that again. If we know that for a caller's server, when that server will be done with that caller, then we know for future callers when the servers will be available for them. So that's what we're trying to capture here. So that you notice that this next service completion time, these two columns, are identical to these two columns, but shifted down by one row. Sorry, these two columns, but shifted down by one row. So the 4477, it shows up here, 4477. So the previous caller ends up setting up the next completion time. So then the next caller, we're looking at that information to figure out when the next server will be available. And so again, we're just setting up relationships between the previous row and the next row. There's no look ahead, there's no look behind, there's no long memory. Any memory is stored within the previous row, and that's it. And then after that, we can calculate our stats because we now know when each caller's service completed, we know when each caller arrived. And so we can calculate the delay that we can say if their service and their arrival time began, like the difference between when their service time began and their arrival time, that difference is their waiting time in the system. And the difference between when they left the system and when they arrived in the system, then that gives us the time in the system. Another little case statement here, though, because we don't have an explicit column for this caller's exit time, because all what we're depending on is we say, okay, which server was chosen for this caller? Okay, when is the next completion time for that server? That is implicitly the time when this caller exits the system. And then we're done. So that is how we go from an MM1 queue in a spreadsheet to an MM2 queue in a spreadsheet. It's the same type of logic, but now we have to expand the logic about which server was chosen, but otherwise most of the rest of it remains similar. But I hope you see it's not trivial to go from the MM1, which is a little simpler, to this MM2, where we got all these case statements, these brackets here. So it's not ideal to have to do this if you have a major change in the system architecture, but it's possible. Questions about that setup? Where you get the MM2? The idea here is not to motivate you that you should use spreadsheets for this. It's supposed to be the opposite. This is why we have tools like Arena. You will be frustrated at the clunky interface of Arena, but if I were to ask you to simulate the networks of systems that you will simulate in Arena with this, it would be much, much worse. Okay. All right, so many types of sims, DES systems can be simulated within a spreadsheet. An interesting thing is that, so we do a lot of sponsored work here. So work for different organizations, industry and organizations, government organizations, and so on. Due to regulations, then, for example, colleagues of mine who do a lot of work with the NIH, DHS, they have certain restrictions on what software their contractors can use. They can only use software that's gone through certain checks. You could argue maybe it's a racket that that throws money only towards certain companies. Maybe it's for security. There's who knows what the reasons are, but sometimes they say, sorry, we know you've learned to do all of this in a Python based framework, but we don't actually allow Python to be used in the organization at all. So go back to these using something else. And so what we find is, like, if for our Department of Homeland Security, we've actually had them, when we ask them, well, what would you like us to make sure our students know if they want a job at the DHS in order to do operations, on airport operations and things like that? Then they'll say, well, it'd be really nice if they knew Visual Basic for applications. And we're like, well, that's kind of archaic, right? But they say, we know several of those sub-organizations don't have the ability to use sophisticated statistical tools, scripting languages, and so on, because they haven't been cleared for use. But what has been cleared is Microsoft Excel and VBA. So when they do all of their analysis work, they have to find a way to shoehorn it into Excel. So, sometimes you do find that even though you've learned how to do things in a more elegant framework, then you have to, that's why it's good to know what's going on behind the scenes, because sometimes you have to implement it for yourself behind the scenes. And that isn't necessarily often, but it does happen. So that is one reason to learn how to do this stuff. But as you can see, it's very cumbersome if somebody comes to you and they say, I want you to simulate this system that has all of these different nodes connected in this different way. You can manage to figure out how to follow all the events through the system. But if somebody comes back and they say, okay, actually, we need to insert one more process into the system, then it might mean a complete rewrite. So it's not sort of ideal. So that's why we're going to move on to Arena. But before we do that, in this lecture and in lab 3, then what we're going to look at is what are some of the useful utilities or applications you can do using simulation, spreadsheet-based simulation. So that's what we're going to start out here on, and that'll set up that lab 3 experience that you're going to be working on this week. All right, questions about the map going forward here? I'm not going to ask you to do any of these spreadsheet simulations like that I just showed you. The lab 3 is on Monte Carlo analysis. That's something I do want you to know because that's like super well suited for spreadsheet applications. You're going to do Monte Carlo runs in spreadsheets. Like a lot of times that's the easiest way to do Monte Carlo analysis. And so that's definitely something I want you to know. But I'm not going to ask you to implement discrete event system simulations in a spreadsheet. But I want you to know how to do it. And I'll give you that bonus credit on homework B1 if you try that yourself. Okay. So inventory management problems, this is one of the key things that you often see people put into spreadsheets, even dynamical inventory management problems. So what do we mean by that? Well, this is going to relate to that muffin sim that we saw last week. So the idea is each day or each hour or each minute, you get a random set of demand. So you're trying to supply a demand, but and every day or every minute, every interval, you know there's going to be some demand on you, and you have to draw from your inventory to supply that demand. So you don't know what the demand's going to be each interval, and you have to stock your inventory so that you can provide that. But you don't want to overstock because it's very costly. If you don't supply enough, that's costly in a different way. But if you supply too much, then that's that could mean that it's opportunity cost. That could mean you have to pay more in terms of rentals space at a warehouse and so on and so forth. So that's the kind of the thing there is that you've got random delays and you need to figure out how much to provide. In the muffin simulation, the idea here is your inventory is actually empty space in the oven. So when someone comes to you with a raw muffin, then that's a little bit like saying, I have a demand for a baked muffin. Well, if they only ever come to you with one muffin at a time, that's your demand distribution. Then if you have an oven that is for 30, then you've probably spent too much on that oven and it's probably taken up too much space. So, you probably could pare that down and try something else. I mean, that exact example, if you like go to coffee shops or whatever, you'll notice that like different equipment will show up on the counters. They're doing exactly that problem, possibly related to muffins. Like you're saying, how many, hot sandwiches do we need to bake at a time? Those sorts of things. That is an inventory management problem where, the inventory is like the empty space inside that oven. And the more space in the oven, the less space on the counter. So the muffin sim is an inventory management problem. Empty spaces is inventory, arriving muffins are demand. Okay, so generally, inventory or demand carries over from period to period. So what that means is, generally speaking, if I need to stock refrigerators that I want to sell, and I stock 12 of them, and somebody comes and buys 5, but that's all they bought that day, then those 7 then show up in the inventory of the next day. And then I need to figure out, do I just leave 7 in inventory or do I buy more? Or do I let that decline into a lower level before I buy more? Those are the kind of the key questions there. So how much inventory do I add to my current stock based on my current inventory levels? Because things carry over from day to day, inventory problems typically have state. So you can ask yourself at the beginning of every interval, what is my current inventory level? So when we talk about a state variable, inventory level is a state variable. It is changing over time, and I cannot answer any questions about today's policy without knowing yesterday's leftover inventory. That's what makes it a state variable. It carries and it changes over time, and we care about its value at any instant of time. And we can use modeling assumptions to simplify some of these to make them functionally static. So for example, we'll see an example of this. We can convert the end of day inventory into a cost and start over. So rather than saying like, well, I'm going to take my 5 refrigerators and try to sell them tomorrow, then you basically write them off at the end of the day and say, I have a loss of 5 refrigerators that I didn't sell. And then you can accumulate those costs. And that's one way to penalize bad inventory management, even if it isn't realistically what goes on in the real system. So that's one way to do it. And so that becomes simpler to implement than dynamical models. But we're going to look at dynamical models and how we can build those. So the first example I want to show you is so these are standard examples, common examples. So if you go anywhere where you do inventory management, then you'll hear about these examples, or at least variations of these examples. So this is the order up to system. So you get these 2 variables. These are your decision variables, capital M and capital N. So M is the target inventory level. So that is the level that, so in this graph, this is this dashed line, M is in Mary here. And so in this jagged sawtooth here, that is the inventory over time. So the idea here is that there is a target level that every inventory renewal period, you look at how much is currently in your inventory and you order enough to bring yourself back up to that level. So N has to do with how long it is between those periods or between those orders. So the idea here is like every day you check your inventory. So in the beginning of the day, you say, how many refrigerators do we have? And that helps you figure out this line here. And this is saying that after a certain number of days, like every 10 days, you say, okay, let's see how much is in the inventory and let's refill. So those are the 2 key decision variables that you have to decide on when you're doing this operations research is how often do I order and how many do I order up to? That's why it's the order up to problem. And there's a lot of different ways you can answer that problem. So you can, and they're coupled. So if you check very often, then maybe you don't need to keep a lot of inventory on hand. But what we're going to see is every time you order, there's got costs that have to be paid. So when you order, the inventory doesn't come immediately. It might take 5 days. It might take a month. So we're going to call it the lead time. That lead time is going to affect your decision. And then also, every time you order, you might get a discount if you order many in one batch. So if you order small batches, then maybe you don't have to order as much, but maybe now you have to pay more every time you order, and those costs add up. So it's not trivial to figure out what the best interval is, what the best N is, and what the best M is. So how do we set up this problem? So I borrowed the problem here from the book. This is, again, in chapter 2. There's also a similar inventory problem we're going to see in lab 7 later in the semester, an SS inventory problem. It's very similar, but slightly different variables that we're choosing here. Inventory, again, is our state variable. It's a dynamic model, so it has state. So the inventory is the state that is changing. So each N days, we order enough to bring the inventory back to M units. That's what I was just saying before. But one of the variables that we have to put in is how many days does it take for the new inventory to arrive? And that is going to actually be an activity. That's going to be an input model. So some days it takes 5 days for new refrigerators to arrive. Some orders take 10 days to arrive. And so we're going to have a distribution of like, well, when I order this, it's just like ordering something on ground shipping. They said they give you a range. They say it'll arrive here between 5 to 7 days. It'll arrive between, it might be overnight, but if there's a delay, sometimes it'll be 2 or 3 days. So there's a distribution of time it takes to actually get the order. So that's something that we have to model as an input. Each day there's a random demand. So how many people come in and ask for a refrigerator? So that's another input that we're going to have to model. So that's another random variable that is driving variation in our system. The lack of inventory leads to back orders or lost sales, but having too much inventory is costly to store. So we need to capture those costs as well. So then, of course, the question is, how do we choose this 2 variable policy that affect the frequency of back orders and lost sales? So the first thing we do in any one of these models is do our input modeling. So I just said what the two big inputs were, the two big random variables. So this is not this is the random variables that we have before we start the sim. We can look at statistics of historical data, and we can say that up here, this is our demand distribution. So every day, people either order one refrigerator, two refrigerators, three refrigerators, four refrigerators, or none. And so for each one of those options, we assign a probability to it. So this is saying 10% of the time, nobody orders that day. 25% of the time, there's one order. 35% of the time, there's two orders, and so on. So that's what I mean by setting up a distribution of demand every day. Now, as you'll see in lab 3, we often will turn these probability distributions into cumulative probabilities, which just sum this up. So 0.1 carries over, but then you add 0.1 to 0.25 and you get 0.35. You can do that game all the way down until this is always equal to 1 at the bottom of the distribution. You'll see the reason we do that is that when you're simulating in tools like Excel or even in MATLAB and others, having that cumulative version of your distribution makes it easier to generate the random numbers that you're going to need to make these demands show up in the right proportions. And that's something you'll start seeing actually as things come up even in the next unit on random variables, but you'll start playing with that in lab 3. All right, so we do the same game down here with lead time. So again, this is the number of days between when you order and when the inventory actually receives the order. So it could be 1 day, it could be 2 days, it could be 3 days. Most of the time, 60% of the time, it's 1 day. Some of the times, 30%, it's 2 days. And the rare 10% of the time, it takes 3 days to get the order. So those are our two input models. So good input modeling versus bad input modeling. I hope you can see the way you choose these probabilities can completely change the outputs you get of the simulation. So even if you've got a beautiful simulation that models all of the processes in the system well, if you get these numbers wrong, your outputs will be meaningless. So that's what we mean by input modeling. Any questions on these input models? What I mean by a demand distribution or a lead time distribution? Okay. So I'm not going to go through this spreadsheet, but this is what an example spreadsheet would look like after it's done. The key thing that I'm going to focus on here is that one simulation run goes over 25 days. So the idea here is I might want to do replications of my 25 days. So this is sort of saying like, what are our inventory cost statistics going to be in a 25-day period? And then I could rerun those 25 days and I could get a distribution across those 25 days. So that's kind of the idea there is you can have, again, variation within a replication and variation across replications. So if we look at just a couple of these columns here, then we can see on each day, we know things like what was my beginning inventory that day? What was the demand for refrigerators that day? Based on the demand in the beginning inventory, how many refrigerators did I end with that day? Did I sell some? But I may not have sold, I may not have been able to sell all of them. So then I have a shortage quantity. How many days did I actually have refrigerators short where now we're sort of assuming that those people could come back and be in our future demand distribution, but we can't guarantee that those sales will come back to us. And so we're going to accumulate those as costs down here. So as you can see here, I can now accumulate these things like you've done in your cumulative statistics in your hand sim. And it says here like ending inventory, there's a sum here of all of these inventories. When I divide by 25, I get an average ending inventory. So on average, every day, there's 2.76 refrigerators left in the inventory. And on average, we get every day half a refrigerator shortage. So those are things that, we might want to minimize this average while also minimizing the shortage quantity. But that's a multi-objective problem. If you have very low inventory at the end of the day, it's going to be a higher probability you're going to have very high shortages. So those are the things as we play with this M and N, it's going to change these averages here. But it's not just the averages. That's the beauty of simulation. Averages are the world of 470. And that's great. The back of the envelope, high school level math you do in 470 is good for quick calculations. But when it comes to real world operations, you need the whole distribution. And so what's nice about this is I can run 100 simulation runs of that 25-day sim. And now I can say, this is the average ending inventory. This is saying that when I look at the average inventory at the end of one 25-day run, I can look at a distribution of averages. So I could actually calculate an average of averages. So this is saying that some of my simulation runs, I had at the end of a 25-day period, an average daily inventory left over of 2. But there were 8 runs where those 25-day runs where they actually were 5. And there were a bunch that are in between 3 and 4. So this shows that even though we've accumulated those statistics over 25 days, that if you rerun those 25 days over and over, you get significant variation there. And so now we can get this distribution of the ending inventories and see that this current strategy, this current MN strategy, could have as many as 5 refrigerators left in the inventory or as few as 2 refrigerators left in the inventory. And even the shape of this can tell us interesting things. So that's one of the nice things about this, is that we get a lot more information. We don't just get an average. We actually can start talking about the shape of this, and we can start talking about risk. Like, is there a risk that we're going to have less than a certain amount in our inventory at the end of the day? What is the risk of that? I see that there's pretty much no risk that we're ever going to run out of, like, that the average over 25 days, there's no risk that the average is going to be 0 over those 25 days. But it also shows me that I'll never have more than 10 in that average over 25 days. So there's a lot more interesting questions I can ask about this distribution. All right, questions about this framing. Does that make sense what we're looking at here? The distribution of averages from a 25-day simulation run 100 times. Okay. So a simpler inventory management problem is the so-called news vendor problem, which now is getting a little old to call it a news vendor problem because we don't talk about paper newspapers as much. It's sometimes also called a single period inventory or a perishable model inventory. And this is the idea that we're going to simplify things by not making things carry over. So it's the idea that the news vendor has got a newspaper that's got today's news, and tomorrow no one's going to want to read it. So whatever newspapers they brought, then they have to sell them all, because if they have any left over, they can't sell them the next day. So this could be bread in a subs shop or something like that. If you make too many loaves of bread, you maybe can't sell them the next day. You just have to get rid of them. Or maybe it's, certain types of produce or sushi or something like that, that you make them the one day and you have to decide how many to make. But if you make too many, you can't use them the next day. So it's a perishable model inventory problem. Because nothing carries over, it's technically, in this simplest form, not a dynamical system. It does not have state, because every day is a new day. So we can then just do stats over every individual day and say, on the average day, how well do things go? And so that's kind of what you would do in a 470 approach, is you'd say, well, what's the average profit? Well, I can say, well, okay, so it's, if every day I've got a certain inventory. So I started the day and I said, I'm going to make this much sushi. I'm going to stock this many newspapers. I'm going to bake this many loaves of bread. That's my beginning inventory that day. At the end of the day, I'm going to know how much demand that I have. Well, the min of these tells me how many of the product I sold. So if I made too few of the inventory, then I sold all my inventory, which maybe will be good on the cost side of things, but that means I'm going to have an unmet demand. On the other hand, if I made too much inventory, the min is going to be demand, and I will only make as much as the demand, and I'll have a bunch of inventory left over. So that's where this min comes into play. So both of these are random variables, and the minimum is a random variable. I multiply that by sales price and take the expectation, and that tells me the average profit. I'm sorry, the average revenue. but then I subtract off how much it costs to make each one of those items in the inventory. And so that way, if I have a lot of inventory, then I need a lot of revenue in order to make a profit. And that's what's being captured here. Now, what's the beauty about all of this is if you know these distributions, so you know that this inventory is a Gaussian distribution, a normal distribution, and this demand is a normal distribution. If you know that, or if this inventory is a static number, sorry, this is our decision variable, the demand, let's say we know that is a bell curve. We know that it's a normal distribution centered around 5 with a standard deviation of 2. Well, it's possible to then calculate what the expected value of this is, because you can look it up. You can take minimums over normal random variables, and you can get a random variable out that has a mean. And so you can turn this into a nice tidy little formula that has inventory as the free variable. And so if I want to optimize this, then I just do old school optimization. I could just take the partial derivative of this thing relative to inventory, set it equal to 0, and I will get the optimal inventory. And that's easy. That's the easy inventory model system. But it turns out that not many systems, any questions about that? To follow the idea here, in this super simple inventory management problem, we can turn it into a simple expression that we can optimize using basic calculus, just setting derivatives equal to 0. That's the basic system. Any questions on that before we get complicated? So the idea here is great, but it turns out that these simplifying assumptions, they don't always fit very well. It's rare for something to be totally perishable. Usually that sub shop is going to sell the day old bread for a little bit the next day. It may not be the same amount. There's all sorts of other complicating factors we can add. And once you add even a few of those complicating factors, you can't do this easy math approach here. So, we also may not want to know just the average performance. We might want to know how often do I make a lot of profit? How often do I make not that much profit? I may not care about my average profit. I might say I need to make at least $100 in a month, or I need to make it, think about it in terms of your rent. Let's say you're deciding to take up a side gig. You're not interested in the average monthly revenue from your side gig. What you're really interested in is, can this thing pay my rent? And that is not an average property. It may make the average may be way more than your rent, or the average might be less than your rent, but often enough, it's actually greater than your rent, even though there are bad days where it's less, where the average pulls the average less than your rent. So knowing like whether I can pay my rent with this is much more interesting than the average. Because if the average is over your rent, that's fine, but that might still mean there's 3 months out of the year where you can't pay your rent. And so knowing that, even though the average month it pays your rent, that there are months that are under average, that's more important. So just this average analysis is often not good enough. So how can we turn this into a sim that helps us get that distribution? Well, let's make it a little more interesting. We'll say we've got a fixed quantity of newspapers Q that will be purchased for resale every day. We have a certain demand distribution that will vary each day. And this is where things will get very interesting in the spreadsheet. And so if demand is bigger than Q, we're making too few papers. If demand is less than Q, we have too many papers, and we can accumulate high costs. So how do we set this Q? Well, the demand distribution for newspapers is very complex, and it's going to require a complex input model, not something that you can easily do in a little calculus-based model. So there are 2 stages of this input model. There's one is, what type of news day is it? Is it a good news day, a fair news day, or a poor news day? Was it right after an election, or was it in the middle of the summer? Those sorts of things are change the type of news day. So what we're saying is there's 3 types of news day: good, fair, poor, and they occur with these probabilities. A fair news day is most common, but it's a good news day is pretty likely, and a poor news day, it happens. So in this case, a poor news day means I'm not going to sell a lot of papers. A good news day is I'd like to sell a lot of papers. Now, what does it mean in terms of D here? There's no D up here. This is just what type of good news day it is. Well, what we're going to do is have a set of distributions that are queued off of whether it is a good, fair, or poor news day. So if it's a good news day, that maps to this demand distribution. So we're saying that we could sell 40, 50, 60, all the way up through 100 newspapers in a day. But how we distribute the probabilities across those days depends on whether it's a good, fair, or poor news day. So it's a two-stage input model where you have to decide what type of news day it is before you can figure out how much demand is in that news day. So it's a very complex input model, but it is much more realistic. If you ask somebody how many newspapers they sell in a day, then they'll say, well, it depends on the day. Like if you ask somebody how many subs do you sell, we're like, was it a Saturday or is it a Wednesday? Is it at 12 p.m.? Is it at 7 p.m.? So these things matter when you're talking about your demand distribution. So you've got this nice complex demand distribution that we can now load up into a sim. So we have a sim here where we've got 20 days. So for every day, we draw a random variable that tells us, is it a good, fair, or poor news day? And then once we know that random number, we can then draw from the demand distribution and say, how many newspapers do people want on that day? And then from there, we know enough to calculate our revenue from sales, our lost profit from excess demand, our salvage from the scrap, the daily cost and the daily profit, and we get a total profit at the end of our 20 days. So in one replication, we get one number to say over 20 days, or you could imagine it's a month if we go to the rent example. So over a month, you make $114 in profit from the newspaper venture. Now, if you have a rent of $100, then you paid your rent this month, but will next month also be 114. So we need to know the distribution of total profits across multiple 20-day simulation runs. So that's what we did here, is that we said, well, let's run 400 20-day periods. And this is what the profit looks like for 400 20-day periods. So sometimes you make as much in 4 out of those 400. So 1% of those times you make as much as $200. But there are some where you're making under $100 in that 20-day period. So knowing this distribution is a lot more interesting than knowing the average. The average is here. The average is whatever this is, like 150 or something like that. But if my minimum threshold for performance is 100, then I have some that are that do not make it to the threshold. So oftentimes when we're optimizing, we do not optimize averages. We do what's called minimizing downside risk. And so we're not quantifying where this star is, where this average is. We're quantifying the area underneath the things to the left of this line. That's our goal. And so we may want to choose our how much inventory we have based on how much is below this line. We might be able to tolerate a lower average if it tightens the distribution and moves things above the line. Likewise, if your average is completely below the line, you might want to maximize variance. That's what we call a stretch goal. And often you talk about it in investing. Animals do it when they're foraging. If it looks like the average behavior is, there's just no way to bring the average above your goal, then you do risk seeking behaviors. So you say, how do we maximize the variation in our profit outputs? Why? If we minimize the variation in our profit outputs, we're guaranteed to lose. But if we maximize the variation, we at least sometimes will win. So ideally, the average would be above the threshold, and then we just want to minimize variance. And it's a bet hedging strategy, because you might want the minimization of variance might decrease your average, but it reduces the amount that is below the goal. So that's why distributions matter, because if you just go off of averages, like often what you'll do in 470, then you'll find that you're missing a lot of the picture, and the actual strategy you need will be much more complicated than that. So questions about that, about this analysis and how it was formed and what you're looking at in this histogram? Okay. All right. Okay, so now I want to set you up for lab 3, Monte Carlo runs. So this is, in lab 3, you're going to do, I think, 2 or 3 examples of these Monte Carlo simulations. A Monte Carlo simulation is a stochastic simulation approach where we use random sampling to estimate a quantity that is impractical to calculate exactly. So examples that I'll talk about on the Lab 3 lecture are like, you can estimate pi. Like if I have a perfect circle, I could measure the circumference of the circle and I could try to estimate the diameter of the circle. And if I look at the ratio of that, I can calculate pi. If I have a Taylor series expansion of certain quantities, then I can back out pi by taking so many terms. There's all these computational ways to estimate pi. Well, it turns out there's a bunch of different ways to estimate pi that if you just throw marbles on the floor, if you watch where the marbles land and count up how many landed a certain way and how many landed a different way, you can estimate pi. And the more marbles you throw on the floor, the better your estimates get. That's Monte Carlo analysis. It's the magic of using random numbers to estimate things that don't appear to maybe even be related to those random numbers. And so you'll see examples of that in Lab 3. Simple examples of that, which are not getting to the numerical estimation, is something like a bombing mission. So this again comes from the textbook. Each bomber carries 10 bombs, but when they drop bombs, they don't land perfectly on their target. So then the question is, how many lay within the area that you care about? And it might be a funny shaped area, like this area here. You can see some lay outside the area and a bunch lay inside the area. Well, when it's a funny shape like this, it's very difficult to calculate this just knowing the distribution of every bomb, like knowing that input model. If I drop a bomb, then there's a bell curve where it could land. Knowing that so-called circular error probability of dropping that bomb is maybe not enough to know exactly how, if I drop 10, how many will be inside this weird shaped area. But I can easily run a sim to do that. So the idea here is every row of a spreadsheet, I generate 20 random numbers, 10 pairs of XY coordinates. So I can say that I know that when I drop a bomb, it has a certain X dimension, a certain X error, and a certain Y error. So I can draw XY coordinates for every bomb of where it fell. And so I will have 20 numbers, 10 XY coordinates, and then I can just count up how many of those in that row landed within the area. If I do that then for a bunch of different rows, then I can estimate the distribution over all of those rows, and then that gives me some idea of how many hits. And so in this case here, I find that I ran 400 bombing missions, each one dropping 10 bombs. So the distribution here goes from 0 to 10. You can't be any higher than 10 because you only drop 10. And what we're seeing here is that for this input model, so for this accuracy of this bomb, then what we're seeing is that most often 7 are inside the area, but occasionally you get all 10, but occasionally you get some where only 2 get inside the area. In fact, yeah, it looks like that's the worst case scenario, so that 2 are in and 8 are out. So that's just a simple Monte Carlo where the rows don't relate to each other. There's no state. Every row is a mission, and then there are 400 rows, which correspond to 400 missions. So for every row, you say, how successful were you in that mission? Then across those 400, how successful were you across the 400? And you get that distribution. Questions about that idea? So that's a Monte Carlo analysis because we're just taking an average across a bunch of random outcomes in order to try to either estimate a distribution or estimate an average number of bombs that land in the area, without ever actually having to do the math that you could do if you knew the distributions and you could try to figure out with this geometric area, how do I do this two-dimensional integral? But with those funny shapes, it's really hard to do those 2D integrals. So instead, you just do the sim. Okay. Reliability problem. So it's actually a very similar idea. I've got a machine that 3 ball bearings. Any one of them could fail at any time. It's very costly to replace 1 ball bearing. So there's questions of, if one ball bearing fails, then do I wait for all of them to fail? Do I just replace all of the ball bearings at once, even if the other 2 are still good? How do I figure out the right choice there? So I can simulate 15 3 bearing sets for 2 different policies. The first policy, replace each ball bearing only when it fails. So I go into the machine, I pop that ball bearing out, and then I just put that one back in. I leave the other two as fatigued as they are to keep on going until they fail. Or I do like what they do here in classrooms. You might notice that it takes a while for them to replace light bulbs in classrooms. It's because it's too costly for them to replace one light bulb at a time. So they wait for a certain number of light bulbs, and then they go and they replace it. This is probably a bad example. It looks like it's a good job here, but that hallway is dark. It takes a while for them to replace things when they burn out because they just don't have the staffing and to pay the cost to replace every little thing. And they need it to kind of get bad enough. So those are the two policies that we're comparing here. So in our spreadsheet, what we're going to do is we're going to simulate. Keep in mind, this is 15 3-bearing sets. 15 times 3, that's 45 ball bearings. So I'm going to simulate 45 lifetimes. So 45 sets of 3 ball bearings, each one of them with their own lifetime. The input model is the distribution of time until a bearing fails. So we're going to take that input model and apply it 45 times. And then we're going to then calculate the delay. We're also going to another input here. There's a delay until the mechanic arrives during each repair. That's an implicit cost because every time I call the mechanic, then the machine is down for that amount of time. So that is going to be something that encourages us to just replace them all, because if they're already out to replace one, if the others are going to fail sometime in the future, I may as well just have them replace them all right now. So those are our two inputs that would go into this. And so I'm not going to, I forgot that I don't have the spreadsheet for this one, but you can imagine how this would go. You simulate a bunch, 45 ball bearing failures. So, and those are grouped into sets of 3. And so, and then we can ask for that 45-day or that 15 3-bearing set, we can calculate the costs associated with these things and see, like, at what point does the delay get so long that it becomes much better in terms of keeping my machine alive or keeping my machine running to just replace all the ball bearings. All right, questions about that example? Another example of Monte Carlo runs. We're just generating a bunch of random variables and taking averages. And then the example you'll do at the back end of lab 3 is this stochastic activity network. The idea here is that you have the model that, our conceptual model is making breakfast, but it could be, there's lots of different networks that work this way. There's 3 things happening in parallel. The problem doesn't get solved until all 3 things are completed. And so the question is, how long does it take for the network to complete? So at the top path, so this is like, making eggs. So maybe there are 3 steps to making eggs. You got to crack the eggs, you have to add milk, you have to fry the eggs. So there might be 3 steps here from start to finish. Each step takes a little amount of time, but there's 3 steps. Now, maybe there's toast. So maybe toast, you have to get it out of the bag and you have to put it in the toaster. Or maybe you just have to put it in the toaster and you have to wait for the toaster to complete. So that's 2 steps. Each step takes longer than the egg steps, but there are fewer steps. Or then there's making bacon. And so maybe with making bacon, it's 1 step, but it takes a long amount of time. Now, if you notice, the average time here, so the average here is 3, 3, and 3. Across all of these paths, the average time is 9 minutes. So our question would be, what is the average time of the network? Is it going to be 9 minutes? And then what path is going to be driving the time for the whole network? Now, when you look at this and think of it in terms of averages, it looks like it's symmetric. The top path is 9 minutes, the bottom path is 9 minutes on average. But if you think through it, the distribution of times on the top path, and I'm going to be asking a question about this in a second, looks like a bell curve. When you add together this time, and this time, when you add together 3 times together, then you get the top path looking like a bell curve. these are all uniformly distributed times. When you add three uniformly distributed numbers together, you get a bell curve. The bottom path is uniformly distributed between 6 and 12. Well, like I just said, it's uniformly distributed. It is not a bell curve. So it's true that the top path has an average of 9 and the bottom path is an average of 9, but the top path's distribution is shaped like this. Anybody have a guess as to why the sum of three uniformly distributed random variables is a bell curve? Do we know something about sums of independent random variables that suggests why it should be a bell curve? 380, 385, three letters, abbreviation, central limit theorem. You're seeing the central limit theorem in action here. When you add things together, they tend to form bell curves because the central limit theorem says that when you add independent random variables together, then the limiting distribution, and it turns out it's very fast, the limit, is a bell curve. This is the reason why the wear pattern on a floor is going to look like a bell curve where the center of that bell curve is sort of the average path of the instructor or something like that. If you picked up carpet and looked at the carpet pads, it would have a bell curve wear pattern. If you look at door handles that people push on, it would have a bell curve wear pattern because every day or every, several times a day, people push on that thing and they add wear, and the wear from one person is independent of the wear of the other person. As they add together, it's more likely that they're going to wear near the middle. It's less likely that a bunch of people will wear near the edges. And that's what we're seeing here is that, yeah, this task could take 4 minutes. This task could take 4 minutes. And this task could take 4 minutes. But it is very unlikely for you to be unlucky at all three tasks simultaneously. Usually, if you take a long time getting the milk out, you probably don't take a long time cracking the eggs. So unless maybe it's just really groggy or whatever, and there's some correlation between them. But if they're truly independent, then the long time here is not going to correlate with a long time here or here. And that's why you cluster around the mean. That's why the central limit theorem works. So now you have these two distributions. Now you see why it's an interesting, I hope, maybe you see, or you'll see in lab 3 why it's an interesting problem, is to ask, even though all three pathways have a 9-minute average, which pathway might we expect to be driving the time of the system? Any guesses of that? When you look at these two things, keep in mind, so we have this one task that must complete in order for the whole system to complete. And then we have this task that also must complete. This is the network, the sum of the tasks. Both of these are happening in parallel. Which one of these things do you think might be driving whether you have to wait for the whole system more? Do you think, in other words, is the lower path more limiting or the upper path? How often do you think you'll be waiting on the upper path to finish before you can leave versus the lower path? Which one are you going to be waiting on more often? How many people think this one you'll be waiting on more often? How many people think this one you'll be waiting on more often? How many people aren't really sure? Okay. Those who said this one, why? So, and just a reminder, this is 6 minutes. This is 12 minutes. This is saying the bottom path is equally likely to take 6 minutes, 7 minutes, 8 minutes, 9 minutes, up to 12 minutes. It's equally likely to take any of these. This one, this is 6 minutes. This is 12 minutes. This one's saying is it's not likely to take 12 minutes, but it can. Not likely to take 6, but it can. Much more likely to take 9. So with that in mind, why might you think you'd be more often waiting on this one? Yeah. That's right. That's what I'm getting at here. So here, like it's very unlucky for you to have a 3-step process and take the maximum amount for all 3 steps. But if you only have 1 step that's uniform, then there's a lot more mass over here. It's much more likely it's going to take 12. So as you're going to see in lab 3, as you start working this thing out, you should notice that as you go from 3-step to 2-step to 1-step, then the critical path, is what we call it in lab 3, is going to be more likely the one that has the fewer number of steps, because the summation process through independent things actually tightens distributions. But when you're not summing, then you're opened up and you have a lot more opportunities. So look for that in your results of lab 3. Look for that skew where you're like, huh, it turns out that I don't take 9 minutes for the system. I actually take 12 minutes or 9.5 minutes for the system. And when I look at it, usually I'm waiting on this single step process. And it's very rare for me to be waiting on the 3-step process. That's something you don't get by only looking at averages. That you only get by looking at distributions. Questions about that? Okay. So that's kind of what we're saying here. How are you going to set that up in the lab? Basically, every breakfast is 6 independent variables. 3 for the top, 2 for the middle, 1 for the bottom. You're going to draw those 6 random variables, and then you're going to say, for that breakfast, which activity took the longest? The sum of the 3, the sum of the 2, or the 1? And then you just say, okay, whoever took the longest, that's going to be how long that breakfast took to make. And then you'll flag who took the longest and how long it took. And you're going to do that for lots and lots and lots of breakfasts, and then take the statistics across those. And you'll get a distribution of how often did each path take the longest, and you'll get a distribution of how long the breakfast takes to make. And what you should find is that it won't take 9 minutes to make, it'll take longer than that. And you'll find that the 1-step process is often the thing you're waiting on. Okay. Questions about any of that before we wrap up? Just a couple more slides. Okay. So, yeah, we can do a lot with spreadsheets, but we operate in complex systems. So you can set a spreadsheet up once, but when your boss comes in and says, actually, I need you to add this, it's, you might mean scrapping your whole spreadsheet and starting over. Opens up the opportunity for errors and so on. So these simulation tools we have allow us to have much more flexible, we can specify things at a high level, let the tool do all the ugly math behind the scenes, and we just have to specify the input models and the basic structures of how things flow from one spot to another. In Arena, the flow is going to look like a flow chart. It's graphical. And then you drill down into each element of the flowchart to specify the input models and configure them. And then you let Arena do all of the math behind the scenes. And that's great, because then if you decide you want to add another complication to your system, you just drag a new block on, wire it up, and then you're done. So that's why we kind of do that, because not everything is the nominal case. Not everything is the simple news vendor problem. There can be drive-throughs that have order stations in sequence or in parallel. And you might be asked, like, oh, now that you've evaluated one of them, then actually we have enough space that we could actually, instead of doing all of the ordering stations in a sequence, then maybe we actually should do it in parallel. Would that be better? And then you'll be asked to do that evaluation. Because, for these sorts of things, it's costly to build these things. They want to get them right, but they may not have come up with all the ideas, or maybe things change in what resources they have available. And so being able to flexibly change from one to the other is going to be important, and not something that you could do inside a simple spreadsheet. And there's lots of other examples too. Adding, the invention of mobile order. That like goes for even when you're not landlocked. You've got a restaurant that you thought is just operating normal, and then suddenly cell phones enter the things, and then you can now start ordering a cell phone. It's as if they built a new door onto the restaurant where orders are coming in, but people who make the order aren't even in the restaurant. So it adds this additional complication of like, do I actually start the order now? Do I have flexibility? If I know how far away they are, can I wait a certain amount of time to start the order later in order to better meet the demands of those in-store customers while still getting the revenue from the mobile orders? I mean, that's a whole new thing, and that requires a completely different model. That's much easier to add in the sim tools you're going to learn than it is if you're trying to build it using a Python script you wrote, or Excel, or whatever. And so I know as you're going to start using these tools a little bit, NetLogo in lab 4 next week, and then in lab 5 after that, Arena. They are not nice looking tools. They're a little ugly, they're a little clunky, but they do make life easier once you get used to using them. All right, so that's why we use special tools. They automate tedious repetitive coding, hopefully reduce errors. They often include high-level components motivated by common applications. So in Arena, they know that the industry that's out there frequently is modeling manufacturing systems with Arena. So there's a bunch of pre-built manufacturing system modules you can just drag in and use. You don't have to build everything from scratch. So that's kind of nice. They usually have graphical visualizations. A spreadsheet list of numbers is not, a nice thing to look at, a nice thing for your stakeholders to look at, but a 3D visualization of how people are moving in and out of a system with stats that are generated on the fly next to it. That's something that is much more compelling. And you often have to tell that story and convince, like, even though you know the math, your stakeholders don't know that. So that's helpful. But I'm not saying these tools that if you've picked up Python, R, Pandas, SPSS, SAS, etc., you'll still use these tools because, as you'll see, despite the strengths of Arena, it has real weaknesses in its data analysis. They're very limited. They're really just meant to be ways for you as an engineer to get a quick idea of what the outputs look like. But I'm hoping that when you prepare your lab reports, once you start using Arena, try not to just use the raw outputs out of Arena. They often don't even have like axes labeled. So if you can, dump that into a spreadsheet and graph it properly, because really Arena is meant to be a diagnostic. It's not meant to be a nice clean output. So that's really what these tools are for. You'll see next week agent-based modeling. After that, you'll start actually doing the discrete event system simulation, and then system dynamics modeling. That's what you see in like 477 if you ever take that course or move on to other sims. Any questions? All right, so if not, then we'll do, I know I had a bunch of opportunities for iClickers, but we'll just do the one here. And I'll do a short answer. All right, should be open. Question is, in the news vendor problem, how much can you sell unused inventory the next day for? So in the news vendor problem, unsold inventory is how valuable is it the next day? And that's all I've got for you. So if you have any other questions, feel free to come up. Otherwise, we'll see you next week. And have a nice weekend. Yeah, in the news vendor problem, how much value does unsold inventory have the next day? Or how much can you sell unsold inventory for the next day in the news vendor problem? And it's graded for completion, not correctness. So don't worry too much about it. Uh-huh.